Today we're going to talk about finding the area between two curves. We've talked about how to find the area under a curve, but today two curves. So it's pretty simple and very similar to what we've already done. If I want to find the area bounded by the curves, which would be the area in between these two curves, the square root of x and x squared, then all I have to do is find the area under the top curve. So the area under the top curve in this case would be the square root curve. So that would be the integral of the top, gives us the area under the top curve, minus, and then if I take the area under the bottom curve, then that takes this area right here. And so if I subtract that space under the bottom curve, all that's left is the space in between the two curves. So this is our goal, the area under the top curve minus the area of the bottom. But we already know that we can put these two functions together into one integral and work it out. So that's what they're saying right here. To find the area of the region bounded by these two curves, we just take the integral of the intersection, which would be here and here, that's 0 and 1, of the top curve minus the bottom curve. So let's go ahead and give that a try. It's going to be the area equals the integral from 0 to 1 of our top curve, which in this case was the square root of x, minus our bottom curve, which was x squared with respect to x. Alright, so that gives us the integral from 0 to 1 of x to the 1/2 minus x squared. So this would be x to the 3/2 over 3/2 or 2/3, x to the 3/2 minus x to the 3rd over 3 or 1/3, x to the 3rd, and we're going to evaluate that from 0 to 1. Alright, so if I plug in 1, I'm just going to get 2/3 minus 1/3, 2/3 minus 1/3, minus, and then I plug in 0, and that's just 0 minus 0, 0. So 2/3 minus 1/3 gives me 1/3. So the area of the little section between the curves is 1/3. You can see the bottom of the numbers. There we go. 1/3. Alright, for our next example, it wants us to find the area between these two curves, but it doesn't give us a diagram. So there are two ways for us to figure out which one of these curves is on the top and which one's in the bottom, because the top one always has to come first. So what we could do is make a sketch. So this is option 1, make a sketch. We know that y equals x squared looks like this. And this is a negative x squared graph, which is going to go the other way. Also, we know here that if I factor out x, this would be 2 minus x. So x is 0 or x is 2. So this graph is upside down and goes through 0 and 2. So it would look something like this. All right, now these don't have to be exact sketches, but this is option 1 to figure out which one is on the top. So in this case, this would be our top, and this one is our bottom function. The other option to figure out which one is on top and which one is in bottom is to set these two functions equal to each other and then solve for x. So I'm going to move it all to the right hand side. So this would be 2x squared minus 2x. Factor out a 2x. So either 0 equals 2x or 0 equals x minus 1. So x is 0 or x is 1. So then, once we know this is where they intersect, which we're going to need anyway, we need to know where they intersect. 0 and 1 are going to be the integral values. But in addition to that, we can figure out, okay, well, at 1/2, for example, what would we get? Well, if I put 1/2 in here, I would get a 4th. If I put 1/2 in here, I'm going to get 1 minus a 4th, or 3/4. So this one is bigger than this one. So this one's on the top and this one's on the bottom. You just pick a value in between, plug it into each one, and see which one is larger. So this is our top, this is our bottom, either by sketch or by analyzing algebraically. So now that we know that, we're going to set up our area function. Our area is the integral from 0 to 1, 0 to 1, where they cross, of our top function, 2x minus x squared, minus our bottom function, x squared, with respect to x. So we can put those together and have the integral of 2x minus x squared, or 2x minus 2x squared. And you could take the 2 out, or you can go ahead and evaluate it as it is. This would be x squared over 2, and then the 2's divide out anyway, so it's probably better just to leave it in there. So I just get x squared. And here I get 2x to the third over 3. And we're going to evaluate from 0 to 1. Oh, again, so sorry. Can't see what I was writing. All right, so 2x minus x squared is 2x minus 2x squared. Then just evaluate each one. So 2x squared over 2, 2x to the third over 3. All right, so now we're ready to plug in our numbers. So I plug in 1, and I'm going to get 1 minus 2/3, minus, and then I plug in 0, and I get 0. So 1/3 minus 2/3 is 1/3. All right, I'm also going to go over right now 2 ways that you could evaluate this definite integral on your calculator. One we've already talked about, another we have not. So one of the ways that we could do this, and this is the one we've already talked about, is to type this function or this version of the function into your calculator, into y equals. So here it is. And then second trace or second calculate the integral I probably should hang on just a second so we can see it. Let me zoom 6 this graph. Okay, so there it is, and it's this little piece. We probably could zoom in just a little bit because I want you to be able to see what happens. You don't have to zoom in because it'll do it regardless, but so that you can see what's happening. So we're going to second calculate the integral from 0 enter to 1 enter, and it gives me my answer. And if I wanted to convert that, if it's some decimal that I don't know, I could go back to my home screen and pull up that answer and then ask it to convert it using MathPrac. Okay, so that's one we already know, but here's another option for you. If you didn't want to graph, then you can go to Math, and then scroll down your choices here until you find function integral, the integral of a function. So choose that one, and then we're going to type in here our function. I'm going to do the shorter version this time. So 2x minus 2x squared, and then we're going to put a comma, and then we're going to tell it what variable we want to use. In this case, it's just x, and then we're going to give it the interval from 0 to 1. 0 comma to 1. Close out your parentheses, and it will give you your answer. So there are two ways to evaluate our definite integrals. And again, this one we could convert using MathFrac as well. All right, so two choices on the calculator to get this answer. Now remember, even if you use a calculator to get the answer, if it's a calculator question, you still must always show the setup, and then you can give the solution. All right, on our next question, it wants us to find the area of the region bounded by the curves of y equals sine x and y equals cosine x from 0 to pi halves. So we're going to go ahead and make a sketch so we can determine top and bottom, and I think on this one we're going to have a little bit of a different type of issue. But remember our cosine graph, we're just going 0 to 1/2, so I'll just draw from 0 to pi. So our cosine graph from 0 to pi halves comes down like this, and then it keeps going down here to pi. The sine graph starts at 0 and goes up, and at pi halves is at its highest point. So it's doing this and then comes back down to 0 at pi. So we're just going to pi halves, that's all it said. 0 to pi halves. But the problem is, this is our cosine curve. This is our sine curve. And in this section, cosine is on top and sine is on the bottom. And in this section, sine is on the top and cosine is on the bottom. So they switch which one is on top and which one is on bottom. So when that happens, you're going to have to break your integral into two pieces, because it always has to be top minus bottom. So what we're going to need is this intersection point, which in this case ends up being halfway through or at pi fourths. Now you can find that intersection, if it's a difficult one, by setting your two functions equal. Sine x equals cosine x. Well, we know that they're equal at 45 degrees or at pi fourths. Or you could set them equal and get the decimal answer in your calculator if it's a calculator question. But what we're going to have to do is, for this first area right here, we're going to do the integral from 0 to pi fourths of the top function, which in this case is cosine x, minus the bottom function, sine x. And then we'll have to add to that this other part over here where the sine is on top. So this would be the integral from pi fourths to pi halves of sine x minus cosine x. All right, so on this one I am going to use my calculator just to evaluate and see what we get here. All right, so I'm just going to use the y equals version. So cosine x minus sine x. We're going to second calculate the integral. From 0 to pi fourths. So that gives us 0.41421356. Plus, and now I do the integral from pi fourths to pi halves, this time with sine x on top. Okay, so we're going to calculate that one. My window's big enough. From pi fourths to pi halves. All right, so again, same thing. So we get 0.828 to 3 decimal places. All right, on example 4, we're going to find the approximate area of the region bounded by these curves. And so we could set them equal, like I said earlier. This one, I'm just going to put in the calculator. So I'm going to show you what I was talking about. If we want to find where they intersect using the calculator, we would put one function in y1, the other in y2, and find the intersection, sketch the graph, find the intersection. So here are our two functions. I'm going to zoom 6. I may want to zoom in on it, but there's the first function, there's the second. So we see this little space in here. So I'm going to zoom in just a little bit so I can get a better picture of what's going on right here in this space. All right, so let me go ahead and make that sketch. So we're talking about this area right here. Okay, so I'm also going to use my calculator to find my intersections. It looks like this one is at 0, but what about this other one? So I'm going to second calculate the intersection. Scroll over there close to that second intersection. Hit enter, enter, enter. And it looks like my intersection is at 1.18077, or 1.181 to, and the y value is 0.763. Now you may not want to round that off to 3 decimal places on a test until after you get to the end, but for this problem, I'm going to go ahead and just leave it with those 3. So we're evaluating from 0 to 1.181 of our top function, which turned out to be this x square root of x squared plus 1, minus our bottom function, x to the 4th minus x. Okay, so I'm going to show you something else that's kind of cool since I've already got these in here. In our y equals screen, I've already got these two functions in y1 and y2. And these aren't that bad. I could retype or just subtract this one out here, but I want to show you something. You can go to vars, which is a key right down here, vars. And when you hit vars key, if you go over to yvars, it has a place that says function. And if you push the function button, hang on, I've got to be, I want to make sure I'm in Y3. So let me do it again. You want to be in Y3, so we're going to do vars, arrow over to yvars, click function, and it gives you all the choices of functions. Well, we're going to pick y1, and it puts y1 in here, minus, and then we're going to choose y2. So I'm going to do the same thing again, vars, yvars, function, y2. And so now y3 in my calculator is the top function minus the bottom function. Now in order for it to integrate, I don't want all of these turned on at once. So what I'm going to do is go over here to the equal sign. And if I'll hit enter on the equal sign, then it turns off those top two. And it won't graph those. It will only graph y3. So now I can evaluate my integral. So I'm going to second calculate number 7, the integral, from 0 to 1.181. There we go, 0.785. So a couple of new calculator skills today, and one of them is this vars. If you have, especially if you have really lengthy functions in here that you don't want to retype, you could always go to vars and just do top function minus bottom. Or if this one had turned out to be the top, y2 minus y1. And that way you don't have to retype everything again. All right, on our last example, it wants us to find the area of the region bounded by these two graphs. And this is an x equals 3 minus y squared and y equals x minus 1. Well, this is a typical function. This one, x equals y squared, is not a function because this is going to be a sideways parabola, and it's a negative sideways parabola, so it's going to be going backwards like this. So what I'm going to do, just to show you what the graph looks like, is go ahead and rearrange this into y equals. So if I move my y back to the other side so that it's positive, I have positive y squared equals 3 minus x. So y is going to equal plus or minus the square root of, I'm going to rearrange these, negative x. I think I'll go ahead and pull the negative out. So negative x minus 3 in parentheses. Now the reason I'm doing that is because there's a couple of things going on here. The negative inside is going to reflect across the y-axis, and then the negative on the outside is going to reflect across the x-axis, and so we end up with this. We know that that minus 3 shifts us to the right 3. This is a square root function graph, so we have the square root, so except that it's reflected. It's not normally it would go this way, but we're reflecting it, so it's coming back this way. So that's the positive square root, and then we've got this negative square root, which is doing the same thing except reflected across the x-axis. So our function looks like that. I think my pen's about to run out of ink. Okay. All right, and we also have y equals x minus 1. So this one. So it's down 1 and then up 1, over 1, up 1, over 1. So it's going to look like this. So our area between the two curves ends up being this space in here. Now, we have a little bit of a problem because top curve looks like the line on most of this picture. But when I get to here, things change because this is my top curve and this is my bottom curve. Now we could still do top and bottom curve and just switch it out once we get here. We could say top curve minus bottom curve, top curve minus bottom curve, and use the positive square root minus the negative square root for this section. But there is an easier way, and that's what this is about right here. If we have two x equals functions, which I could make this easily, x equals y plus 1. So if I have two x equals graphs, then I could go from right to left, right being positive, left being the negative, so our furthermost to the right minus left, right minus left. And instead of going from x to x, go from the y value to the y value. So we do need to know where these intersect. And to find the intersection, we can set these functions equal to each other. Sorry, I had to switch out my pen here. All right, so I'm going to set this equal to this. So y plus 1 equals 3 minus y squared. So y squared plus y minus 2 equals 0. And then factor it out. Y, 2, 1, plus minus y equals y equals negative 2, y equals 1. So this is when y is negative 2. This is when y is 1. And if we wanted the x values, we could plug that back in. if I put 1 in here, 3 minus 1 is 2. This is 0.21. And if I put negative 2, let's just use this one, negative 2 minus, sorry, in here, that's a y value. Negative 2 plus 1, negative 2 plus 1 would be negative 1. All right, so I have these as my 2 points, but these y values, since I'm integrating with respect to y, these have to be y values on my integral. I usually do with respect to x, and it's x's. With respect to y, I need to use y's. So this area function would be the integral from negative 2 to 1 of my furthest right function, which was this 3 minus y squared function, minus the left function, y plus 1, with respect to y. All right. And you can type this in the calculator as an x function and evaluate it, or you can do it by hand. Either way, even though this is y's, once you type it in with respect to x, it will still evaluate the same way. All right, so here's what I'm talking about in the calculator. You can just type it in as 3 minus x squared minus x plus 1 and evaluate it in the calculator. So we're going from negative 2 to 1, and we get 4.5. All right. So remember that if you have functions, sometimes these can even, like we could rewrite this one, and we could have done it as two separate integral intervals, one from negative 1 to 2, and then from 2 to 3, and then top curve minus bottom curve, top curve minus bottom curve. But it simplifies if we do just right minus left using the y values and using the y equals, the x equals functions. So your choice, but just know that you can do right minus left just like we can do top minus bottom.